go. Okay. This is Exam 4, Chapter 6, Thermochemistry Review, Part 2. And my notes tell me that we made it up to number 23. So unless we need to backtrack, we'll pick up from there. Let's see. Fresh marker. This one. Okay, do you have anything that's a burning issue?
Not at the moment, no.
Okay. You holler and stop me if something comes to mind.
Okay.
Let's see. Let me see if we've done any like number 24 yet. No, we haven't. Don't believe. So let's pick up number 24. How much heat is required to raise the temperature of 5.75 gram sample of iron? So we have the mass of iron. All right. We expanded the student representation by 100%. All right, this is part 2 of our review. So we're up 24, and the mass of iron in our sample is 5.75 grams. The specific heat of our iron is 0.450 joules per gram degree centigrade. The initial temperature is 25 degrees. And the final temperature is 79.8. Okay. And the question is, how much heat is produced? Actually, how much heat is required to raise the temperature from here to here? All right. So the formula this is really simple. I mean, once you get the information up here and understand the question, then you can go to your formula. So for this process, we only need this one heat unit, Q. So we can use that straight formula just like it is. S then would be 0.450, and I'm going to put all the units up this time just to show that they cancel. And we're kosher. Mass is in grams already, so we're good there. Now we need delta T. So delta T is always final minus initial. Right? So the final temperature is 79.8 degrees minus 25. Okay. So we've done all our thinking. All that's required now is crunch numbers. Well, let's see, let's be sure. Grams on the bottom, grams on the top, that cancels. We're good there. Degree C, cancel. And we're left with joules, which is the unit for heat. So we're good. Now we just need to crunch numbers. 0.45, 5.75 times that. And then we need to find the difference here. 79.8.5 is 54.8. So that difference is 54.8 3C. And it's a positive value, right? Because this is the final and that's the initial. The difference gives you a positive. So that times those two. And I get, let's see, 143 significant figures. 141.795, which rounds off to 142. So let's see if that's one of our answers. Yep. Turns out that one is E. Okay. It's good we did a simple one like that, because when we start putting Q's together, you need to be able to do this for each individual Q. Then when we have to add them together, remember in our isolated system, all the Q's total up to 0. This is just one of the Q's for that slug of iron. Then when we start doing things with that iron, maybe put it in a calorimeter with water, something like that, then you have to start adding Q's together in that system. Let's see if this one works better. And there's nobody zoomed in yet. D. I just looked at the corona map this morning and I don't see any cases in West Virginia. You heard of any? No.
West Virginia.
Yeah. Good. Maybe the mountains will protect us. Okay. So let's see. Let's see how this one operates. Didn't do 25. Well, why didn't do 25 in the word problems? Maybe I better put that one up there. See if there's something to it. 25. That's black. Two metals of equal mass. Two metals of equal mass. So we have metal 1 and metal 2. And they have equal masses. Right? So M1 equals M2. Equal masses. Different heat capacities. All right. So S1 is not equal to S2. They have different heat capacities. And they're subjected to the same amount of heat. So the Q1 equals the Q2. We add the same amount of heat to each one. They're the same mass, but they're different heat capacities. Okay? Remember the units here. Joules per gram degrees centigrade is heat capacity. Specific heat capacity. Okay, conditions. Which undergoes the smallest change in temperature? Okay. So if these two Q's are equal, that means that if we expand these terms, right, where this one equals S1, M1, and delta T1, S2, mass 2, and delta T2. Okay. Which undergoes the smallest change in temperature? Okay, the masses are equal, right? So So they're essentially constant. We don't have to worry about the masses. These are both constant. We just need to know what happens to these two, right? Because these are different. Okay? So if these two terms, if this side is equal to that side, and let's just arbitrarily say that S1 is greater than S2. Let's go to our choices. How about that? Let's do our choices. So A says the metal with the higher heat capacity undergoes the smallest change in temperature. The higher S smaller delta T. Okay. B, metal with a lower heat. Okay, so this is the converse. So the one with the smaller specific heat capacity would have the smaller delta T. C says both undergo the same change. Same delta T. Is that one even reasonable? They've got different heat capacities. The delta T's have to be different. Right? So we can throw that one out right now. How about D? You need to know the initial temperatures of the metal. Initial T's required. Is that true? Or can we say something about the delta T's without knowing their initial temperatures? Well, let's look at the conditions. Different heat capacity, the smallest change. Actually, it doesn't tell us what their starting temperatures are. It doesn't tell us that they have the same starting temperatures either. Yeah, just the same amount of heat, the same mass, different specific heat capacity. Okay, we got one vote for A. Got one for A. Let's see, you need to know which metal you have. Do we need to know the exact metal? No, I mean, it could be any metal, as long as they're different. Right. Need metal ID. We don't need that. We don't even need to know the initial temperature. So it's got to be A or B. So let's look at these conditions. If the M's are the same, they're the same. Now we only have to consider what happens to one if the other one changes. Right? So if these two are different, how are these two related? Remember when we said Boyle's law for today? The product of two variables equals a constant. What type of relationship is that? Inverse, yeah. So we can use that same logic for this one. If this one goes up and that one goes down, this one starts here and goes down there. This one starts here, that one has to go up. If this one goes down from here to here, if that's a decrease, then this one has to increase for them to be equal. So the one with the higher S, if this one, let's say it goes the other direction, that way, that way. If this one goes up, which is what this is saying, then this one has to go, this one goes up, this one has to go down, up, down. So it is A. The higher S is the smaller delta T. Now that's purely mathematical, right? From a physical perspective, what does the S mean? The S is relating what happens to the relationship between the amount of heat required to raise the temperature 1 degree centigrade. this one is big, then it takes a lot of heat to raise the temperature 1 degree centigrade. If this is small, the same amount of heat will raise the temperature a whole lot. So let's take a practical example. Our previous one was iron, right? It had an S equal to that, numerically. Whereas water, this is iron, whereas water is 4.17. Right? The heat capacity of water is much higher. So when you add some heat to water, temperature only changes a little bit. You add heat to iron, temperature goes way up fast. Or if you have a ceramic, have you ever seen videos of those ceramic cubes that they use to make the space shuttle tiles? Yeah, they're very light and they have a very low heat capacity. They're probably like 0.001 or something like that, really low. You can heat them with a blowtorch or stick them in a muffle furnace and run the temperature up to 600, 700, 800 degrees centigrade. And pull them out with your bare hand. Well, you probably don't want to stick your hand in the muffle furnace. Pull it out first. Then you can grab it by the corners and just hold it there, and it's glowing red hot. Because it may be hot, the temperature may be high, but there's no heat there because the specific heat is so low.
So what's the difference in, like, you know how you get like aluminum pans to put in the oven, and then you have your metal pans? It's like aluminum is never as hot. Like you can usually touch it as soon as you set it out.
Let me think. I don't have my textbook with me. See what the specific heat is for each one.
I can look it up.
Yeah. See if that's true. If aluminum is a lower specific heat than iron, then that would explain it. The other explanation is possibly the rate of heat loss by conduction to the air. Could be higher for one metal than another. And that's a different topic altogether.
So they're pretty thin, and then the ones you have.
Yeah.
That you don't throw away.
So the mass is different also. Mm-hmm. Yeah. Right. I mean, iron pan could be the same thickness as the aluminum pan, and aluminum's going to be lighter, right? Because it's only 27 grams per mole, whereas iron is 56 grams per mole. It's a heavier, denser material. So the mass would vary for the same volume. Yeah, they start building up variables there pretty quick, don't we? Okay, that's 25. Okay, mark that one off. Can't mark it up for this one because it's not there. Let's see. 26 looks like we've got a calorimetry problem. So that would be worth tackling. We won't do our calorimetry lab until we come back from spring break. We'll do the Boyles today, and then when we come back from spring break, we'll have the calorimetry lab, and that's when the Boyles lab will be due. Okay, a 32.5 gram piece of aluminum. So mass aluminum is 32.5 grams. The molar heat capacity. Right? So in this case, I'm sure if the symbol changes for that, let's put a little N here for moles. The molar heat capacity for aluminum is 4.03 joules per degree C mole. Right? So the only difference is we've substituted moles here instead of grams. It'll be a different number, right? because it's not grams, moles. Let's see, who was that that chimed in? Ah, Kessa. She must be sitting in the doctor's office. Zoom. She won't be here for that, unfortunately. Okay, let's see, where was I? Okay, and is heated to 82.4 degrees. So it's the initial temperature of the aluminum is 82.4 degrees. Okay? And it's dropped into a calorimeter containing water, and the water has a specific heat capacity of, let's see, water. Specific heat capacity of 4.18. Actually, that's not more. The water is just specific heat capacity of molar. Joules per gram degree C. And its starting temperature for water equals 22.3 degrees C. The final temperature of the water equals 24.2. There you go. Calculate the mass of water in the calorimeter. All right. We could approach this two different ways. Probably the best way is, let's see how I did it in here. Okay, that's fine. If we're going to use this value, then that needs to be converted to moles. The other way you could do it is leave that way and convert this to joules per degree mole. But to do that, you'd have to use the molar mass of aluminum, because this value is specific to aluminum. Now, the way I did it in the work problems is I left this, I left this alone and converted that to moles. But either way will work, because all we need is, this is our starting formula. So the Q of the aluminum plus the Q of the water has to be 0 in our calorimeter, because it's isolated. What happens in our calorimeter stays in our calorimeter. Okay, so now we just need to expand that formula. Okay, so what is the Q of this one? Well, let's see. We need our molar heat capacity for aluminum times the moles of aluminum times our delta T for aluminum. Right? And then we add to that what happens to the water. So this one for water times the mass of water times the delta T for the water. Okay? There are two Qs. This one for aluminum is in terms of moles, and this one for water is in terms of mass. It really doesn't matter, because this is going to reduce to joules, this one reduces to joules. You end up with joules in both cases. But first, we need moles of aluminum for this one to work. Right? So, sorry, I'm going to have to erase that. We need moles of aluminum, so that means grams on the bottom, moles on the top, and then we need sign in. Aluminum 26.98 is the molar mass per liter. 8. Right? So this will tell us how many moles of aluminum there are. And that value will go like this. 32.5 and 26.98. 1.205 moles of aluminum. Okay? Here we go. This one is going to use that value for aluminum. Joules per degree C mole. And then moles of aluminum, 1.205. Okay, so the moles cancel here, we're good there. Now we need change in temperature. So final temperature minus initial temperature. What's the final temperature of the aluminum? It's the same as the final temperature for the water, because they're both in contact and we wait for equilibrium, right? So this one is the same temperature for water and aluminum, 24.2. Everybody see that? So we got 24.2 degrees for the aluminum minus the initial, final minus initial, 82.4. Okay. So that's the expansion of this one. Now we need the expansion for water. So the specific heat for water is 4.18 joules per gram degree C. What's the mass of water? That was the question. We don't know the mass. That's the unknown. The mass of the water. Okay? And then we need a delta T for water. So the final temperature of water is 24.2, same as the aluminum, minus its initial temperature, 22.3. Okay? There we go. That plus that is 0. Okay, so let's resolve what we can. 0 equals, what's the difference here? We'll just do that as a separate calculation. 24.2 and then subtract 82.4 is minus 58.2. Okay? Then the minus that times 1.205 and then times 24.03. So I get for the aluminum term, I get minus 1685.25. Don't throw away decimals unless you have to. That's correct. And this is joules, right? Because moles cancel, degrees cancel. So we got joules there. Now for the water, what happened to the water? Well, let's see, what is this term right here? 24.2 minus 22.3. That's a plus 1.9. And that's times 4.18. That's as far as we can go with this one. 7.942 times the mass of water. Now, how do we find out what the unknown is? do that? Because we don't know what this one is. You can't add them together yet.
Oh,
What you do is you have to get the unknown on one side of the equation.
yeah, that's what oh, the zero, okay.
So if that one stays there, and we bring this one over here, it becomes a positive, right?
And then you can bring this down to 1.
Right. So now it's a positive on this side is equal to that one times the mass of water. Now we can say this one is equal to that one divided by this one. Right? Or the proper way to say it is divide the whole equation through by 7.1942. That makes this side 1, and it puts it over here. Divided by 7.2 equals the mass of water equals. Let's see. Good, still in my calculator. I get 212. Let's see. Yeah, 212 grams. There, let's see if that was one of the answers. It's A for number 26. Okay? That seems like an awful lot of work just to find out what the mass of the water was in that container in our calorimeter. But the best way to not make mistakes, put everything you know up here from the problem, extract it from the problem in a list of some kind. Then you can see what you have and then look at the question. What's the question? The mass. Right? So the mass of water was our unknown. I should have put that down there before. Mass of the water, that's what we're looking for. So then you should recognize that what we've got going here is a calorimeter. Right? We drop that aluminum metal into water, watch the temperature change. That's a calorimeter. That means that we have 0 equals Q aluminum plus Q water. And then we expand. This is what the Q aluminum would be, and we're using moles here because the specific heat is in terms, it's the molar specific heat, the molar heat capacity. Moles, not grams. Right? So that's why we had to set it up this way. That times moles times change in temperature. And we had to convert this to moles so we could put it in here. And there's that value. And then our change in temperature is always final minus initial. If you do it the other way around, your sign will be reversed and your answer will be wrong. So you gotta delta T is always the final minus the initial. That never changes. Okay? So we're still going through the thought process here. For the water, we have what happens to the water. And here it is, its specific heat, the unknown, the mass, and then its temperature change, final minus initial. The other trick that we had to recognize was the final temperature of the water is the same as the final temperature of the aluminum. They're together in the calorimeter. And we just watch the temperature change until it stabilizes. Then we know that they're both at the same temperature. And from that point on, it's just number crunching. Everything up to that point was your brain working, hopefully. And from here on, it's just punching numbers into the calculator correctly. Okay, any questions on that one? All right. 26. This one's stubborn. It does not want to come off. 26. Okay. Let's see how we're doing on time. We've already used up a half hour. Let's see if there are any in here that we really need to focus on. 27 is another calorimeter problem, so we'll skip that one. 28 is also another. The difference between the two is you have, you're looking for different terms, but you're using the same logic as our calorimeter logic. 0 equals Q1, Q2, Q3, as many Qs as you need. An isolated system like that, calorimeter, everything has to add up to 0. Let me see. Well, 27, what we're doing is we're using the unknown as the specific heat. And in this case, in this problem, C is the specific heat. Right, so don't get confused. Sometimes C is used as the variable. Sometimes S is used. I think your book uses S. So that's why I've been putting S on the board instead of C. But when I learned this stuff decades ago, C was the specific heat, little c. S actually is a better choice. It's just that I haven't made the change in the problem set. Okay. And then use the specific heat to choose which one of these metals is the one that was part of the experiment. 28 is another one. Let's see, 29. Okay. I want to be sure that we can't afford to use up any money. We got 40 minutes left. So let me hold 29, and if we have time, we'll come back to it. I want to be sure we get all of our bases covered. Number 30, the only trick there is when it says 282K, 306K, it's the same as degrees centigrade. The size of the unit of a K is the same as the size of the unit of degree C. So if you subtract the two, you get degree C. Okay. Subtract 1K from the other, subtract degree C from the other, same thing. 31, let's see what's that. '31 should take just a couple minutes. And it's good to do these types of problems that don't require calculation. They require you to think. So consider this reaction. Hydrogen gas plus oxygen gas yields H2O. And the delta H, the enthalpy for that one, is minus 286 kilojoules. All right. So probably the first thing you notice is we use the fraction here as a coefficient. And that's okay, because the ratio is the same. 1 to a half to 1 is the same as 2 to 1 to 2. But if we had 2 to 1 to 2, then we have to double that value. This is in terms of 1 mole of hydrogen or 1 mole of water as a product. So let's see. Which of the following is true? Okay. A, the reaction is exothermic. Is that true? Remember, everything is relative to the system. What's the system? The reaction is the system. So if the negative, that means heat is leaving the system to the surroundings. exothermic. Okay, so that one's true. How about heat? Well, they can't both be true. It can't be exothermic and endothermic. Let's see. The enthalpy of the products is less than that of the reactants. Enthalpy, the delta H, of the products is less than the delta H for the reactants. So what does that mean? If we say that this is exothermic, that means this heat value is a product. So it would be sitting out here as like that plus a certain amount of heat. Okay. So that means that the heat content of this side is greater than the heat content of this mass, minus that heat. Because now the heat is out here rather than in here. Think of this as an equality symbol. All this has to equal that. So there's more heat in the reactants than there is in the products. That's true. So we got 2 true so far. How about D? Let's see. Heat is absorbed by the system. Can that be true? No. That's the same as B. So E, A, and C are true. So that would be the answer you put on a test, because those 2 are true. Okay. Let's see. Oh, I skipped 32. Why did I do that? In the work problems, I skipped 32. In the lab, you mix 2 solutions. All right, let's skip that one too. Simply because we don't have time to do every one of them in detail. We still have time for the lab. So let's see, what is 33? Yeah, that's too simple. We've done one like that already. 34. 34 is just solving for an unknown in a calorimeter experiment. Let's skip 34. 35. Have a lot of the same kind of problems in here. Okay. Let's hold 35 in. I think we can do that. There's time. Let's look at the back and work forward, because I want to be sure that we catch everything that's important. Okay, we still haven't done a Hess's law yet. Several of those. And, okay, I think I saw one in here that I want to get to. Calculating the calorimeter constant. I saw one. We haven't talked about the calorimeter constant yet. I'm sure that, yeah, here it is. Here we go. Okay, we look at 52. Let's see if that's what I think it is. Yeah, 52. So this one, for this one, we're going to calculate the calorimeter constant. Okay. What do I mean by calorimeter constant? Up to this point, the isolated system that is our calorimeter, we've just ignored the container itself and the thermometer you stick in there, the heat capacity of the styrofoam itself. And it does have some, and the thermometer does have some heat capacity. So when you actually do the experiment in the lab, you've got to account for any heat that's absorbed by your calorimeter or released by the calorimeter into the system. Okay, it's part of the system actually. So what we have is we still have 0, but we have maybe a couple of Q's like we've done before, plus we have a Q for the calorimeter. Okay, that's the only term that we're adding. The difference is these two guys are the specific heat times the mass times the delta T for each one. I'm not going to write that. But this one, the S and the M are combined. You don't necessarily need the mass of the calorimeter. You don't need to know its specific heat. You just need to know what are they together. And when we put them together like that, that's a big C for our calorimeter constant. Right? So if this term, the calorimeter constant times the change in temperature, is supposed to be joules, it needs to be heat. Right? That means this one is degree C. And what does this one have to be to give you joules? It has to be joules on top, degree C on the bottom. So the units for our calorimeter constant are just joules per degree C. Mass doesn't even enter in. Okay. All right, so now let's get to this problem. Let's see. I'll leave that up there. Maybe I'll change the subscript if the problem requires it. 52. The heat of combustion of benzene. So this is our reaction, benzene, and we're going to combust it to yield products. Right? It doesn't really matter what that is. The heat of combustion is negative 41.74 kilojoules per gram of benzene. And we have a mass of this much of benzene. That's the symbol for benzene. The mass of our benzene is 2.82 grams. And the, let's see, combustion causes a temperature rise of 3.29 degrees C. So it actually tells us that the change in temperature is 3.29 degrees C. It increases by that much in the calorimeter. What's the heat capacity of the bottom calorimeter? So the question is, what is that value for a calorimeter? Right? In this case, we only have one Q for the reaction. Right? So it's the Q of our reaction plus the Q of the calorimeter. Okay? Those are the only two terms that we have information for. That's all we need. Okay, so let's expand this one out. So the Q of the reaction is what? What is the Q of the reaction? Well, In this case, we're talking about a chemical process rather than a physical transfer of heat, which we've been talking about up to this point. The Q of the reaction is how many grams times the delta H, the enthalpy. Right? That will give us so many kilojoules. But we need to convert that to joules. Right? So this many grams, so this Q is this many grams, or mass. Let's do it this way. The mass of our benzene times the delta H of our benzene. Combustion, actually. So the curveball that they're throwing at you here is you just need to recognize that Q of the reaction needs to be in joules. So how do you get joules? Well, you're given this value and you're given that value. So if you multiply this one times that one, you get joules, kilojoules. So what we need is delta H in terms of joules, right? So it's minus 41.74 times 10 to the third joules per gram. Right? Because a kilo is 1,000 times. That's what this is. That's a kilojoule. So I just pull that 10 to the third out. And then, of course, if we reduce it, 4.174 times 10 to the fourth joules per gram. What's this one? Well, this one is the calorimeter constant times the change in temperature, right? Because it's joules per degree C. So we need to know the change in temperature here. All right, so 0 equals this mass, 2.82 grams times negative 4.174 times 10 to the fourth joules per gram. Okay. There's our reaction term, and now our calorimeter term is, that's our unknown. We don't know what that is. But we do know what the change in temperature is, don't we? Positive 3.29 degrees. So that means the final temperature is higher than the initial temperature. Positive 3.2 degrees C. Okay. Now that's all the thinking's done. We just solve for the calorimeter constant. Okay. So let's see. What is that value? 2.82. Oh, we're going to have time for one more problem after this. 4.174. So I get negative 1.177. That's 10 to the fifth joules plus 3.29 C. Okay, so we have to bring this one over here as a positive, right? One second. And then we can divide by this one. We'll do this in one step. And this is 3C. That's equal to C. So we should divide that value by 3.29. So I get 3.58 times 10 to the fourth joules per degree C. Now let's see if that one is that one of our 52. Okay, it's in kilojoules, right? So what is this in kilojoules? You just take 3 of those and put them over here as a K. 3.58 times 10 to the first. Kilojoules. Very good. Now, is that one of them? All right, they're in standard notation. So what's that in standard notation? 35.8 kilojoules per degree C. That calorimeter has a huge constant, calorimeter constant. That is a monster. So I'm thinking that they used an especially strong bomb calorimeter, they call it. That is, you can react things that are extremely exothermic, and the calorimeter will hold itself together. It won't fly apart. It's not made of styrofoam. So you have to take into account a very large calorimeter constant in this case. So once you find out what that value is, then you can do any experiment here, plug it in here, and find out what the delta H is for your reaction. Right? Once you've determined the bomb calorimeter constant, then you can work backwards with any other reaction you want. Because as long as you don't change the parts of your calorimeter, like you don't grab another top from a different bomb and put it on there, okay, all bets are off. But once you've determined that for your calorimetry, you keep your parts together. It's the same for our calorimetry experiment we're going to do when we come back from vacation. Once you determine, one of the first things you're going to do is determine the calorimeter constant for your styrofoam calorimeter. And then you can do your experiment. You got to know that value first. Okay, and that's in the method, so I'll give you the method. Let's see. This is the last time we're going to need it. So I need to give you that method today, so you'll have it. Okay, I'll do that between you. Any questions?
You said the reason why we go from the negative to 1.177, and over that, you said it's just like a plus factor. The reason why it goes from negative to positive, so you can get a positive thing.
That's because I moved it over here. See, there's an equal sign.
Oh, that's right.
It came over here.
Distribute it. Okay.
Yeah, that's negative on that side, it's positive on this side. Yeah. And then, once this is over here, I've got 3.29 times C, so to solve for C, I just need to divide both sides by 3.29. And then you get the value for C. What I was saying was, I was going to do this in normally 2 steps, I'll do it in 1 step. So, I'm just trying to save time. Now, let's do a Hess's law. Remember Hess's law? What does Hess's law depend upon? It depends upon the fact that the enthalpy of a reaction is a state function. Doesn't matter how you get there. So your target equation can be the summation of 2 or more individual reactions and their delta H's. Then once you've got it arranged with your component reactions to give you the target reaction, then if you follow the rules, you can just add the enthalpies together. It doesn't matter how you get there. You could go like that, like that, like that. Here we are. Doesn't matter. It's a state function. So let's pick one that's more or less doable. We don't want to do one that's completely off the wall. I'm not going to do any A, B's, and C's either. Let's use real stuff. It's not too drastic. Hard to do with the ones I gave you. Okay. So let me see if I can find the one that's the least painful. That's 65. That one looks like it's not going to cause us too much harm. Okay. 65. All right. We're given these two equations. Now, this does take some thought. That's okay. We can do it. We're given these two equations. Solid and half of an oxygen gas yields solid. And the delta H, standard delta H, is minus 144 kilojoules. And we're also given, so that's 1, 2, given this one, yield copper plus 2 oxide, and its delta H equals plus 11 kilojoules. The question is, what's the enthalpy change for the formation, for the standard enthalpy of formation for this one? We want to know the delta H for the delta H of formation. Remember when I talked about what they mean by formation? This is the first trick. You got to know what they mean by what's the heat of formation. You start with the product, CuO. That's the product in its standard state. And there's only 1 mole of it. That's common to any heat of formation. The product is 1 compound, and it's always in its standard state, standard temperature and pressure. Standard temperature for a solid 25 degrees centigrade. Pressure is 1 atmosphere. So it's 1 mole of that, and then how do you get there? You get there from the elements. Right? So you need copper in its standard state, and you need oxygen in its standard state, diatomic gas. Okay? Then you put in the coefficients to give you that 1 mole. Right? So we've got 1 copper here and 1 copper here. We're good. Oxygen. We only need 1 oxygen. Right? So we put in 1/2. That's the target for our heat of formation, that equation. Right? So we need to rearrange these to give us that. So let's look at the first one. Let's see. First one has no copper in it, but it does have oxygen. Okay, so we got oxygen, and it's on the proper side. Right? So this one's good with 1/2 a mole of O2. We don't have to change that one. As long as we can rearrange this one to cancel everything out except what we need to have. All right, so we need this one. We need copper oxide. So there's a copper oxide. There's 1. Let me be sure I wrote those correctly. Cu2. Okay, so we only need 1 of these, right? So if we leave this one on that side, we're going to end up with 3 of them. But if we put that one on this side, it'll cancel 1 of them and leave us with 1. Is that going to be okay? Well, yeah, because it also puts copper over here. And it puts Cu2 copper 1 oxide on that side to cancel this one on that side. Okay, so if we just invert that one, plus CO yields Cu2O solid, and we change this one, right? It's now negative kilojoules, right? Because the heat evolved, or the heat absorbed in this reaction is the same as the heat evolved in the reverse reaction. So let's just change the sign. If we reversed it. So now we're going to use this one plus that one. So we'll do it longhand. Let's say this one, okay, plus 1/2 O2. And then we're going to put this one in here, plus this one. That's going to yield what's on this side, 2CO, and plus Cu2O. Yeah. Okay. Now let's see. We've got one of these over here and one of those over there. Gone. We got this one here, got that one there. We got this one and 2 of those. So this one's gone and only one of those is gone. So that leaves us with this equation. That being the case, now we can add this one plus this one. All right. So that would be what, 155? Delta H for that reaction. Let's see, is that one of our answers? 65. Yep. B. Okay. The trick to this one is to understand the question. The question said, what's the standard heat of formation? It didn't give you a target equation. You got to know that the target equation is that. Right? So the standard heat of formation for this is 1 mole of that, and then you work from the elements to get there. That's really 2 problems in one. Okay, we only got 5 minutes left. Is there one we haven't covered that I can get to in just a few minutes? Otherwise, we'll talk about Boyle's law and go in the lab. No? No problems? Okay. Let's erase this. And then, actually, I shouldn't have to talk about Boyle's law because you've already put all this stuff in your lab notebook. You're ready to roll. So what are we looking at with Boyle's law? Pressure and volume, right? Okay, so pressure and volume is a constant. All right, so when we go in the lab, we're going to be taking measurements. And the measurement we're going to get is with our 2-liter bottle. There. We're going to have a cap, and we're going to have a valve in it. Okay. Just like a tire valve on your car. And we're going to measure the pressure with a gauge. Right? We got a thing that sticks out here like that. inside, since these bottles are clear, we're going to have a syringe in here. I chopped off the edges so it fit through the hole. And then we're going to have a plunger in there. And you're going to start off at, I think it's 10 minutes. Or somewhere around 10 minutes. Here's our. Okay, but we have to cap the end here. Right, we got to trap the air inside. If we don't, it's just going to equalize and that plunger is not going to move. So what we're going to do is pressurize that bottle so that this plunger drops down to less than 2, maybe 1.5 mils down here. And then we're going to measure the volume against the pressure. Right? So your data is going to look like this. This is going to be in milliliters. This is going to be in pounds per square inch. And this is measured pounds per square inch. Okay. So you're going to start with high pressure and low volume, and go to a low pressure and higher volume. So you're going to have a pressure of maybe, well, I don't know, 60 psi, something like that. And then a volume of maybe 1.5 mils, something like that. And you're going to take measurements periodically until you get down to maybe 1 psi, and then whatever it happens to be, maybe 8.5. Is that your final measurement? Your final measurement is 0 psi. Take the cap off. If you have to, turn this thing over and use that little nipple. Be sure it's empty, and then take the cap off. And at 0 psi, you're going to have something over here, maybe 9. If you started at 10, you're not going to get back to 10 because of friction. Right? It's not going to let it go all the way back out. So that's why we start at high pressure and go to low pressure. If you did the other way around, then you'd have to pump and then measure, and then pump and then measure. This way, you only pump it once, up to the high pressure, and then you just release the pressure as you need. So we got all these values, pressure against volume, but that's not what you graph. You graph the total pressure. So what's the total pressure? It's this pressure converted to atmospheres plus barometric pressure, right? Because there's still pressure bearing down on this. So the total pressure is whatever you measure plus whatever is squeezing that bottle, barometric pressure. Right? So we have to look at the barometer and get that pressure, and it'll be the same. You'll add the barometric pressure to each one of your measured pressures. But they have to be the same units, right? So the most convenient way is to convert this one to atmospheres and convert the barometric pressure to atmospheres. And that way, your total is in atmospheres. Okay? That's the one you plot, this one against that one. And what are you going to get? Let's see. Volume is the dependent, pressure is the independent. What are we going to get if you plot? If you plot that times that as a constant, what do you get? You get a straight line? No. You get a curve, right? Like that. In fact, it's a special kind of curve. It's called a hyperbola, which means this tail gets closer and closer to the axis, and this tail gets closer and closer to the axis, but it never touches. It goes on to infinity. It never touches the axis. All right, so that's what you get with your plot of the raw data. But scientists hate curves. Right? We like straight lines. So how do you get a straight line out of that? Well, if we take this, that, with a constant, and we divide both sides by V, right? That gets rid of it on this side. Like that. That's a little hard to see a straight line in that. So this is a constant, and that's a variable. Let's do this. There's your constant. There's your variable. Y equals mx plus b. In this case, b is 0. Right? So now if you plot p against 1 over v, right? So you're going to have another column over here. Right? It's going to be milliliters to the -1 power. Right? Anytime reciprocal, -1 just means it's reciprocal. Right? So if you plot this as your x, well, actually, kind of backwards, isn't it? That's y and that's x. So we should have p up here and 1 over p down there. Either way, you get a straight line. And the slope is your k. Okay? That's basically the whole lab right there. You just have to really, what are the safety concerns here? Right. Pressure is the bear in the room. So you don't want to, and that's why I always use, these bottles have never been used for this experiment before. Once they're used, throw them away. Because each time you expand track, you have to do it 2 or 3 times. You stress the system. It's kind of like airplanes, right? When they go to altitude, the skin stresses under pressure inside. They only let it happen so many times before it goes through a complete inspection. The X-ray, everything. By law. Okay. So, any questions? Let's see, I need to get a calorimeter lab. So I'll go get that. The lab's open. Just don't forget to turn the lights on so you can see what you're doing. And then you can worry about this later. Once you've got all your data, you can decide how much money you're going to charge the people that aren't here for the information. There's nobody there watching, so that joke was wasted.